but a lot of it is review, and there are no new mechanisms. So our review topics are hydroboration oxidation of alkenes. So we will review this reaction in class. We also need to remember some stereochemistry things. So syn and anti relationships in a ring. So if you have a ring, if you have two substituents, I guess it doesn't have to be on a ring, but it's easiest to see on a ring. If you have two substituents on the same side, that has a syn relationship. Whereas if you have one substituent coming at you and one substituent going back, that is an anti-relationship. So let's remind ourselves of stereochemistry, right? When we have that kind of colored in wedge, that means it's coming out towards you. And then the dash means that it's going away from you. We will be reviewing more stereochemistry after exam 1 because it becomes more important for later reactions. So it's a good time to start remembering this. And then cis and trans relationship of alkenes. So similarly, when we have an alkene, if we have two substituents that are on the same side of the alkene like this, that's called cis. And if they are on opposite sides of the alkene, that's called trans. So this is different than like an alkane, right? If you only have single bonds, you can rotate about the single bonds. So it doesn't matter that much what orientation they are. But when you have double bonds, we cannot rotate about this double bond. Therefore, cis and trans are actually different stereoisomers. Okay, so that is going to become important for one of the reactions that we're going to learn today. So we have 4 learning objectives, but the first one is just review of what we've been talking about. And then the next 2 are 2P reactions. So you do not need to know the mechanism for them. They'll just introduce a couple new reagents for the formation or reaction of diols. So that's kind of the theme of today's lecture is diols. So 2 different alcohols. And then we'll just briefly kind of cover thiols at the end to finish up chapter 16. So let's start with our first learning objective, 16N, which is the 2 Ps for the formation of diols through reduction of dicarbonyls. So this is section 16.5. So this is just a review learning objective, basically. So remember that a diol is going to be any compound that has 2 alcohols in it, right? Di means 2, all means alcohol. So we're talking about the formation of compounds that have 2 alcohols in it. So this first learning objective is just saying that of the reactions that you previously learned to make alcohols, if you can do it twice, you can get diols. So let's look at an example of that. If, for example, we have a dialdehyde like this, 1, 2, 3, 4, 5 carbons, right? This is a dialdehyde. We could reduce this to a diol by just reducing each of the carbonyls separately. So how have we learned to do this? You've learned you can use hydrogenation, so H2 plus a metal catalyst like nickel or palladium or platinum or ruthenium, right? Any of those metals will work. So that would be one way to reduce two carbonyls down to a diol. You also learned sodium borohydride in an alcohol solvent like methanol or ethanol. You also learned lithium aluminum hydride, and then a second step, water, right? And if all of those work for aldehyde to alcohol, they will also work for dialdehyde to diol. So this is just a review of the reagents that you've learned. So these are all reductions. And then just as a note and as a review, we could go back from the diol back to our aldehyde doing oxidation. So if we remember the conditions that we have used for that, we have to stop at the aldehyde, right? These are primary alcohols, primary alcohol, because this carbon has 2 hydrogens on it. So if you use too strong of an oxidant, it will go up to the carboxylic acid. So we have to use PCC or the Swern oxidation in order to stop at the aldehyde. You cannot use something like sodium dichromate with H2SO4 and water, because that would give the carboxylic acid. Okay, so this just shows that if you can do it twice, you can do it twice, right? And that is a way to form a diol from a dicarbonyl. But this is a dialdehyde, right? We can also do this from a diketone, for example. So let's look at an example for that. If we had a diketone, once again, we could reduce, so this reduction down to our diol. And the conditions are exactly the same that I showed on the last slide. Because in the reduction direction, aldehydes and ketones react the same. So, right, we just add, we're forming these extra CH bonds or bonds to hydrogen, which means you're reducing it down. When we go in the oxidizing direction, we can use the same PCC or Swern oxidation. But now we can use stronger oxidants. So we could use something like chromate, sulfuric acid, and water, right? Because the kind of rule for that is that we'll oxidize as much as possible. But once we get to the ketone, it can't go anymore. And so it's already oxidized as much as possible. And so that's kind of the difference between aldehydes and ketones. For ketones, you don't really need to worry. You oxidize it, it's going to stop at the ketone. And so this one can't make our carboxylic acid. So it's okay to use in this case. Okay, so for the dialdehydes, if you want to oxidize up to an aldehyde, you can't use the chromate in water, but for ketones, you can, because it will oxidize all the way up. Questions on that? That's just like a review of the reactions that we've been learning in this chapter so far. Okay, all right. So one way to make diols is just do the reactions that you've learned multiple times. Let's learn some other ways of making diols. So that's our next learning objective. So this was making diols from reduction. So our next one is making diols from oxidation. So this is 16O. So the 2 P's for the formation of diols through hydroboration, oxidation, from alkenes, or with osmium tetroxide. Also 16.5. All right, so this is now forming diols, so 2 alcohols in the same molecule through oxidation from alkenes. So this hydroboration oxidation, this is a 2301 review. So this is chapter 8.8. And in the context of this diol lecture, this is making a diol from 2 different alkenes. So again, it's doing the reaction you've already learned, but doing it twice. So my example here, have 1, 2, 3, 4, 5 carbons. So we have 2 different alkenes. First, we do hydroboration. So we use BH3THF as our reagent. And then oxidation is a second step where you use hydrogen peroxide and base, sodium hydroxide. And that gives you 1, 2, 3, 4, 5. It will add an alcohol to the less substituted carbon in each case. So as a reminder, again, you've learned this reaction before. The first step, BH3THF, does the hydroboration part of it, which means that it adds that BH3 across the alkene. So you can see one of the hydrogens from BH3 ends up here, and then the BH2 ends up here. As a reminder, this has anti-Markovnikov selectivity, which means that the boron ends up on the least substituted carbon. So hopefully that sounds semi-familiar from 2301, anti-Markovnikov selectivity. That's what's special about this reaction, that it gives you that anti-Markovnikov selectivity. And then the second step essentially just replaces the boron with an OH. Okay, you just oxidize that boron off and you just replace it with an OH. So again, we're just doing the reaction twice because we have 2 alkenes, therefore we get 2 alcohols in the product. Yes?
If you were doing this for like a synthesis, would you have to specify that you were using like excess of your reagents, or would you just be able to just write it?
Yeah, so oftentimes, like, you don't have to worry too much about it. Like if you write what I wrote here, that is correct. You would do the reaction that you want to do. Good question. Okay, so that's review. 2 alcohols from 2 alkenes. Our new reaction today is from 16.5. So this is now a diol from 1 alkene. So instead of doing one reaction twice, we're going to do a different reaction to get 2 alcohols from 1 alkene. So for example, we start from 1 alkene. So this is ethylene. This is the most simple alkene. We're going to use osmium tetroxide, so OSO4, with tert-butyl peroxide and tert-butanol. And this gives us 2 alcohols from 1 alkene. So we have 1 alcohol on each carbon. This is a special type of diol that is called a vicinal diol, which just means that vicinal part means that the 2 alcohols have a 1-2 relationship. So we have an alcohol, we have 2 carbons between them, and then another alcohol. So if you know Spanish, I think one of my postdocs likes to say that vicinal reminds her of vecino, which means neighbors in Spanish. And so it's kind of the oxygens are on neighboring carbons. So that's one way to remember the vicinal diol. Just as a fun fact, this molecule right here is what is the molecule in antifreeze, ethylene glycol. And this process, because we're adding 2 different hydroxyl groups, is known as dihydroxylation. So di means 2, hydroxylation, adding OH groups. So dihydroxylation. We've added 2 OH groups in a single reaction. Okay, so that's kind of one of our new 2P reactions. You don't need to know the mechanism of this, but just osmium tetroxide, tert-butanol, and tert-butyl peroxide gives this 1,2 diol. So with the example that I gave you here, it's the most simple example, so there's no stereochemistry. But in this reaction, stereochemistry matters a lot, actually. So if we were to do this reaction in a ring, got our osmium tetroxide, tert-butyl peroxide, and tert-butanol. So I'm going to do a dihydroxylation. So I need to add 2 alcohols. So if I were not worrying about stereochemistry, I would just draw it like this. But this is not fully correct because stereochemistry matters, because this reaction does a syn addition. So they should both be on the same side of the molecule. Okay. So you have to pay attention to the stereochemistry of your alkene and then make sure that you're doing a syn addition to that. I think it's a little bit easier when it's in a ring because your alkene basically has to be cis, but that's not always the case. You have to be a little bit careful if your alkene is not in a ring. So let's look at an example of that. So we'll start again with a cis alkene. If we were to do this reaction, so osmium tetroxide, tert-butyl peroxide, and tert-butanol. Okay, my hint to you, this is the strategy that I use. 1, 2, 3, 4. Draw the backbone of your molecule exactly the way it's shown in the starting material. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, so I haven't drawn in the alkene part, but I drew the backbone in the same orientation. So up, over, down. Now I'm going to do my syn addition. So I need both of my groups to be on the same side of the molecule. OH, OH. Okay. So the reason that this is challenging is when it's not in a ring, it's possible that you can rotate about that center bond. If I were to rotate this molecule such that my backbone is in a different orientation, right? So you can see how I went from kind of this more cis orientation to this more trans orientation. My stereochemistry would then be up on the 2 carbon and down on the 3 carbon. These 2 molecules are the same. All I did was rotate about that center bond, which I know can be difficult to visualize. Model kits are very, very helpful. If you want to come to office hours, I'm happy to work with a model kit with you. So the biggest mistake that we see people make is that they will draw the backbone like this, and then they'll try to do the syn addition, but you can't do that because it's already rotated, okay? So that's why I recommend always draw the backbone in the same orientation as the starting material, because then you'll make sure that you'll do it correctly every time. You just draw the backbone in a weird orientation, it's much more difficult to visualize that stereochemistry. Does that make sense? Questions on that? Yeah.
So the final answer B that we rotated around.
No, this is fine. Okay. Yeah, you can. Both of these are correct because they are the same molecule. It's just much easier to see this. I'm just illustrating a point that you can't just rotate willy-nilly because this I think is much harder to see that you did a syn addition because it looks like they're anti, but you did do a syn addition. It just looks weird. Yeah, but either one is totally fine. All right, let's go backwards with a chime-in question to see if this is making sense to people. Okay, so here I've given you the product. We're doing the same reaction. So the reagents are that osmium tetroxide, that tert-butyl peroxide, and tert-butanol. Tell me which one is the starting material. Again, feel free to chat with your neighbors. Anytime you're going backwards, I then recommend going forwards to make sure you get to the product that you wanted to. Maybe 10 more seconds, get your answers in. All right, see what we got. Nice. Okay, good. So most people are getting it. B is the correct answer. The next most common was C, which is just that stereochemistry difference, which again, I understand where that comes from, is that this is the most challenging part, is the stereochemistry, but it is B. So let's look at why that is. So you were asked for the starting material, you were given the reagents, and you were given 1, 2, 3, 4, 5, 6. Okay, so first thing I would do, number the carbons. 4, 5, 6. Next thing I would do is notice that these two groups, right, are already in that syn orientation already, right? If they were not in a syn orientation, I would then rotate the molecule such that they were in a syn orientation. But now that they are already in a syn orientation, that means that I want the backbone geometry to be the way that it is. So I'm going to draw the backbone exactly the way I have it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the important part here is especially right here. Here, here, here. I want that to look the same. The orientation of that is the same, right? And then in this reaction, the diol came from an alkene. So we need carbons 2 and carbon 3 to be part of the alkene. So then I just add in the alkene there. Okay? The most important thing is like figure out the orientation of the backbone to give you syn addition, and then draw the backbone the way that it is. Don't rotate it. Okay? So that was the most common mistake, is that people were drawing what was it? 1, 2, 3, 4, 5, 6. But that right here is not the same orientation as it was in the product, right? So this cis alkene would not give this product shown. The stereochemistry would be wrong. Questions on that? I know that that is the most challenging part of this reaction. Okay? All right, so that's the first new reaction that we're learning. So we just learned a bunch of different ways of making diols, either from doing reactions you already know multiple times, or doing this dihydroxylation that kind of gives you 2 alcohols in one step. So now let's look at a new reaction that you can do from vicinal diols. So this is our next learning objective, 16P. This is the 2 P's for the formation of dicarbonyls through oxidative cleavage of vicinal diols. which is section 16.11. Okay, so in our first learning objective today, we showed that if you have a diol, you can oxidize it up to a dialdehyde or a diketone using all of the reactions that you've already learned. This is a new reaction specifically for vicinal diols, right? So again, vicinal diols are kind of a special case. So if we take the example that we made from this ring, right? So using that osmium tetroxide, we could have made this vicinal diol here. Okay, I'm going to number my carbons so we don't lose carbons. Okay, so this is a vicinal diol because the alcohol or the hydroxyl groups are on neighboring carbons, right? Vicinal diols. Our reagent for this is periodic acid, so HiO4. Periodic acid. Okay, so what we're going to do is we're going to cut the bond in between the vicinal diol. Again, I'm going to draw my backbone in the same orientation. 1, 2, 3, 4, 5, 6. Okay, we cut that bond and we turn each of those alcohols into an aldehyde or a ketone. So we oxidize up without losing or gaining any carbons. That's the key. Don't lose or gain any carbons. You just cut it in the middle and you get, in this case, a dialdehyde. And then in case you're curious, the inorganic byproducts that we mostly don't worry about is HiO3 and water. So we can get those out with an extraction, but that is the balance of the reaction. All right, so let's break down this name of this reaction a little bit, just so we understand where it's coming from. So we already know what vicinal diols are, right? So that's neighboring alcohols. Cleavage means that we are cutting the bond, right? We are breaking a bond. And then oxidative, here, oxidative means that we're oxidizing the alcohol to a carbonyl. So hopefully that is a descriptive term, right? Because we are oxidizing and we are cleaving a bond. So you got to cut the bond and you got to oxidize up to the aldehyde or ketone. Okay, so let's notice that these were secondary alcohols and they gave us aldehydes. So now let's look at an example where we have one secondary and one tertiary alcohol. So this carbon has a hydrogen on it, so that's a secondary alcohol. This carbon does not have a hydrogen on it. This is a tertiary alcohol. We're going to do the same reaction. Let's double check that they are vicinal to each other. We've got oxygen, carbon, carbon, oxygen. So they're oxygens on neighboring carbons, so they are vicinal. We add that periodic acid. So we're going to clip the bond in the middle. Okay. And oxidize the left side. So this purple hydrogen is right here. And then we're going to draw the right side and oxidize that. So our secondary alcohol, again, turned into an aldehyde. But now our tertiary alcohol turned into a ketone. Yeah, so this, we'll do this in a different color. Oops. So this is tertiary, so that's this carbon right here. And then that purple carbon is right here. Okay, you see that? When we cut the bond, that allows us to then oxidize up. If it was a secondary alcohol, such that it already had a hydrogen on it, it becomes an aldehyde. If it's a tertiary alcohol, such that there's no hydrogens on it, it becomes a ketone. And that will always be true for this reaction. Questions on that? Cut the bond in between it, oxidize it up. Oxidative cleavage. Okay? Why might we want to use this? Okay, so let's look at a multi-step synthesis example of why we might want to use these reactions, and especially these reactions together. So if, for example, you wanted to make something that looks like this, so that is a dialdehyde, right? We have two different aldehydes in this molecule. So my first instinct might be, oh, I could make this through, oxidation of two different alcohols. I like kind of like what we've been doing this whole chapter. So what would I get if I did that? So maybe I could do this and then this. So that would be one carbon, and we've got 2 carbons. It's not symmetrical, right? This is not necessarily an easy compound to make. And so this is actually very, very expensive. So could it be done? Yeah, it could probably be done, but there's an easier way. So this is where oxidative cleavage becomes very, very important. So instead of trying to figure out how to make this unsymmetrical diol, we can think about, well, what happens if I do an oxidative cleavage? So if those 2 aldehyde carbons had been connected in a ring, and I had done oxidative cleavage to make this dialdehyde, what would that look like? So I'm going to number my carbons. 1, 2, 3, 4, 5. Okay, so that's going to be a 5-membered ring attached to this 6-membered ring. So that would be the 6-membered ring, and then I need a 5-membered ring attached to that. 1, 2, 3, 4, 5. And then attached to carbons 1 and 5, that's where my alcohols are going to be, because that is the bond that I had to clip during the oxidative cleavage, right here. So that's this bond here. So this is our vicinal diol. And because we learned how to make vicinal diols from alkenes, we can go one step farther back using that dihydroxylation. So again, I'm going to draw the same skeleton. All that's different is instead of having 2 alcohols, we have an alkene. So we could do a dihydroxylation on this alkene. So this compound is called indene. It's commercially available. It's pretty cheap. 2 steps, we can get to that kind of unsymmetrical dialdehyde. And so this is why these particular reactions can be so powerful, because you can make these very complex molecules pretty quickly. So if we were then to draw this pathway in the forward direction, because remember, anytime you do a multi-step synthesis, you're always going to draw it in the forward direction, but I would figure it out from the backwards direction. So you would start from indene, our commercially available starting material, like so. Then we're going to do our dihydroxylation, which has the osmium tetroxide conditions. Now that I'm going forward, I need to make sure that I give the proper stereochemistry, because this is a syn addition, remember? When I was going backwards, it didn't matter, because that's not what I was worried about. But in the forward direction, it is a syn addition, so you need to remember that. And then finally, we're going to do our oxidative cleavage using periodic acid. to form two different aldehydes like so. And that's unsymmetrical. Okay. Questions on any of that diol stuff? You now have learned multiple ways of making diols and then reacting with diols. Okay, but it's very, very similar, right? It's very similar, yes. So yeah, so if you used PCC on this, right, it would just go to the ketones and it would not cleave. So that's basically what I was saying on this pathway, right? To go from here to here, I could use PCC. That's true. The problem is that this molecule is quite hard to make. Not impossible, but harder, right? And so it doesn't mean that it would be wrong, right? There might be a way to get there, right? Depending on what you're starting from. But as organic chemists, part of what we're trying to do is like have enough tools in the toolbox to find the most efficient route to get places, right? So yes, you could do it. It's just way more expensive, right? And so if that's what you got to do on an exam, that's okay. Sometimes we see people do like really crazy routes on the multi-step synthesis. If it works, fine, right? But like from a practicality perspective, we're just trying to train you to think like, oh, the first thing you think of might not be the most efficient route. So just trying to have some like flexibility in your thinking and be like, oh, what other reactions do I know? What else could I do? That kind of thing. Yeah, great question. All right. Yes. You have a question?
Does it have to be
So osmium tetroxide is always syn addition. There are other reactions that are anti-addition, which we will learn later. But for now, osmium tetroxide is always syn addition. So this one, it doesn't matter. You just haven't learned any reactions that would do it the other way. Yes, because there are ways of doing that. We just haven't learned them yet. Yeah, great question. Other questions? All right. Our last learning objective for today is just briefly introducing that sulfur is a thing and that it is going to become relevant later. But for now, we're just going to introduce diols. This is 16Q. Does not look like a Q. There we go. We're going to explain the physical properties of diols, especially relative to alcohols. So this is 16.12. So we're not covering all of this sulfur part of the book, but we just wanted to introduce this to you because it is going to become relevant when we start talking about ethers and thioethers coming up. So a thiol is just the sulfur version of an alcohol. So it has an SH instead of an OH. So versus our alcohols, right? So this whole chapter has been about alcohols. So we're just going to compare them a little bit just to give you an idea. So a couple of important differences between thiols and alcohols. For thiols, there is less/no hydrogen bonding. Therefore, it's going to have a lower boiling point. Right? So remember, boiling points are affected by the intermolecular forces. So alcohols have hydrogen bonding, right? Such that their boiling points tend to be a little bit higher. Thiols don't really have hydrogen bonding, or if they do, it's very, very weak. So they have much lower boiling points. That hydrogen on the SH, on that thiol, is also more acidic than an alcohol. So for example, ethane thiol versus ethanol. So ethane thiol is what they add to natural gas to make it smell like rotten eggs. That's what ethane thiol is. The pKa of ethane thiol is about 11, whereas for ethanol, it's about 15. Remember, lower pKa means a stronger acid. Okay, so that's just because sulfur is a much larger atom, right? If we look at the periodic table, sulfur is below oxygen, so it's a much larger atom. So its overlap with that tiny little hydrogen is not very good, and therefore it's easier to lose the hydrogen. And then the last thing that we want you to know is that thiols are more nucleophilic than alcohols. So this will become important later when we actually start working with some reactions to make thioethers, for example. Sulfur is more nucleophilic than alcohols. That has some implications on its reactivity and its side reactions, for example. But we're going to leave it there for now, and then we will come back to this concept of oxygen versus sulfur as we continue forward. So that is all I have for you today. That ends chapter 16, and that's the end of the content for the exam on Wednesday. So best of luck studying, and good luck on the exam.